Okay, here we go. This is the introduction to the Laplace transform. And we're going to discuss a mixing problem. We've already worked with one compartment mixing problems back in section, I think it was 3.2, and we're going to do that again, but we're going to add a little complication to basically see the power of the transform, how it can take a kind of a difficult problem and turn it into an easier one. And we're going to run through and actually use the transform. You're going to really have no idea what's happening, but it's going to be quick and painless. And then we'll get to an answer and you'll notice it's the same answer that you get without using the transform. So yeah, so we're going to solve a valve feeder mixing problem. And the big idea with a transform is it takes a complicated differential equation and turns it into an algebraic one. Okay, essentially what this means is we're going to knock years off of the methods used to solve these things. So I don't know how long it's been since you guys have taken algebra before, but probably a couple of years, I'm guessing, or maybe more. So we're going to go back to that level at some point. Of course, you'll have to use a table to kind of help us out. We're going to, in the next section, we're going to build the table up. Not all of the table, but we'll build up some of it so we can use it. And then we're going to turn problems into algebra, which is kind of exciting, especially after what we've just done. And I can tell you this, it's relatively simple algebra too. So it won't be too bad. All right, so once we get the solution in this algebraic world, we're going to take that solution and then we're going to translate it back into the real world. Okay, so we have two worlds. We're going to switching between two worlds. Our world we're going to call the t domain or the time domain. The world we transfer to is called the S domain, or sometimes it's referred to as the frequency domain or the Laplace domain. And we can do all the simple calculations there and then bring them back. So let's take a look at a problem. This is a mixing problem for a valve feeder. So let's take a look at the picture. Fix that up. Let's first get a sense of what's going on. This is a one compartment mixing problem. All right, let's look at the part. So first of all, there's 1,000 liters of brine solution in the tank. There's 6 liters per minute getting pumped in as long as valve A is open. Right now, valve A is open, valve B is closed. Okay, 6 liters per minute is getting pumped in, and the salt content in that mixture that's getting pumped in is 0.04 kilograms per liter. So you'd want to multiply those two to get the flow rate of the salt going in. Now, if we switch this and we turn this feeder upward, it'll turn off A, turn on B. The B is flowing in at a rate of 6 liters per minute, and the concentration of that salt is less. It's 0.02 kilograms per liter. All right, so we got a total of 6 liters per minute that's pumping in, but we also have 6 liters per minute that's draining out. Okay, so if we start with 1,000 liters of brine, of mixture in there, is that ever going to change, or is that going to increase in size and in volume? It's going to stay the same. You got 6 liters per minute pumping in, 6 liters per minute pumping out. So, all right, now we're going to let X represent the amount of salt in the tank at time t. Okay, so let's say we have an initial condition, and let's let X of 0, the amount of salt in the tank at time 0, be 30 kilograms. Okay, all right, so that's the setup. Now what we're going to do to complicate this is we're gonna switch valves after a certain amount of time. So starting at t equals 0, valve A is going to be turned on, and it's going to be turned on for the first 10 minutes. Okay, and then at the 10-minute mark, we're going to turn it off. We're going to turn valve B on, and we're just going to let that valve run forever. So you get the idea? Okay, so what you want to do when you run across any one of these problems is kind of look at it, try and gain a little bit of intuition. Like, for example, you might want to ask, okay, well, what's going to happen over time? Is all the salt going to drain out eventually or not? What do you think? No, I mean, for the first 10 minutes, you can kind of expect the salt to get at least closer to 0.04 kilograms per liter in here, the concentration in here. And then after 10 minutes, you can expect it to approach 0.02 kilograms per liter in here. By the way, you know how to find the concentration of salt in here, right? How do you find the concentration of salt at any time t in there? So inside the tank, how would you find the concentration of salt at time t? What would you do with x and 1000? Nothing? You just divide them. Remember this? We'll give you the concentration. Yeah, it's the mass divided by the volume. Okay, that's how you find concentration, right? Okay. All right, so let's see. So yeah, we're gonna find the amount, we're gonna solve for this function, right? That's the whole point of differential equation, is to solve for the dependent variable. All right, yeah, so this is a one compartment mixing problem, but it's definitely more complicated because we've got this input that's changing. So what we're going to do next is we're going to solve this the old way. And I'm not going to show you every step. We're just going to set it up. And then once we get to that part of the solving part, you're going to actually solve it in your discussion post for this week, or one of the discussion posts for this week. And yeah, you'll have to read that. We'll talk about that in a minute. All right. So let's solve without it. So if you remember how this setup works for these mixing problems, you have your model. It's a first order differential equation. You have to find the input rate and the output rate. The output rate's easy, right? The output rate, you just take the 6 liters per minute times the concentration in the tank. That'll tell you the flow rate of salt leaving the tank. There it is right there. So the flow rate of salt leaving the tank is 3x over 500. Is that part okay? All right. Now the input's a little more complicated because it changes after 10 minutes. So what we can do is we can introduce a piecewise function. But before we do that, let's find, where are we? Let's find the flow rate of salt going in for each valve. So multiply 6 times 0.04 to get the flow rate of salt for valve A being open, 6 times 0.02 for the flow rate of valve B being open. And then what we can do is we can create a function that models this for the first 10 minutes and then after 10 minutes. Is that okay? All right, so this is the flow rate in the first 10 minutes. That's the flow rate after 10 minutes. All right, so let's see, we've got it. So we'll just take our model here. We'll plug in our input rate now, which is the G function, which happens to be piecewise. All right, we'll leave it as a G for right now. So what we're being asked to solve is this first order IVP. Now the issue here is that this guy itself is piecewise. We've never done one of these before, but there's nothing stopping you from solving it. In fact, this is how you would do it. You basically break it down into 2 different IVPs. You'd solve the first IVP for the first 10 minutes. I mean, you know, the initial condition starts off with 30 kilograms. So just go from 0 to 10 and solve that IVP. Of course, you'd want to use, you know, the methods that we've learned before. Now, for the second IVP after 10 minutes, you just change that to a 12. But the problem is we don't have the initial condition. We don't know how much salt is in the tank at the 10-minute mark. However, we can figure it out. I mean, all you have to do is solve this one. And that'll give you an exact solution, right? This gives you a bunch of solutions. But then once you use the initial condition out of all of those solutions, it's going to pick the particular one that you want. And then all you have to do is plug 10 into that. It'll tell you the amount of salt at the 10-minute mark. And then you'll use whatever you get out for the initial condition of your second IVP. Is that okay? Okay. All right, and yeah, the reason why this works is because, salt doesn't just magically appear. It's a continuous function. So x has to be continuous. All right, so now if you do the work and you solve both of them and then you join them together, what you end up getting, this is what you get for the first IVP. And then this is what you get for the second IVP. And if you plug in 10 into both of them, you'll notice you get the same value out in both cases. So they're continuous. So that's the solution. All right. So in your discussion post this week for the section, I want you to solve this thing. And I mean, it's first order, right? It's a first order differential equation. So you might think, okay, well, we should use the methods of chapter 2, I believe, right? So what were our methods of chapter 2? I think there was 3 that we focused on, right? What were the names of them? Give you a hint. One of them, separation of variables. What were the other 2? Yeah, another one was using the integrating factor, solving linear first orders, and then the other one was solving exact equations. Yeah. Yeah, so then in chapter 4, that was for second orders, but then did you guys notice that the methods of chapter 4 could also work on third orders? We've done a few third orders, right? In fact, I think we did a fourth order in the last section in your homework. So the question is whether or not it works on first orders. Can the chapter 4 methods be used on first order equations? They can, yeah. And so that's what I'm asking you to do in the discussion. Basically, you're going to find a YH and a YP for each of these and solve that way. And all it does is it makes the problem much easier, but the theory is completely the same. Okay. So by the way, chapter 6, which is what we skipped, which is what was covered, I've taught in the past. Usually I cover it. It basically talks about that, how you can extend this up to solving these equations basically of any order. And I don't really think we need to do that. So I think it's better that we focus on other stuff. All right, so if you graph this function, put it in Desmos, it's going to look something like this. So you'll notice for the first 10 minutes, it acts like this function, which is exponential. And for the next, after 10-minute mark, it acts like this function, which is also exponential. All right, so that would be the previous way of doing it. And that's fine. The difficulty is going to be solving these guys. As you know, this takes a lot of time. Well, let's look at another way to do this. If we introduce the Laplace transform, turns out we can solve this thing a lot easier. All right, so first kind of the idea. The idea with the transform is you take a function in the time domain and you transform it into another function in the S domain. Okay, so you're going to take little f of t and you're going to transform it into another function, capital F. The capital F is designating that you have applied the transform, but you'll also notice that we start in the t domain and we end in the S domain. Now, as far as what it is, we're going to formally define it in the next section, but I'll give it to you right now. That's what it is. All right, we've worked with these types of integrals before. Do you remember what these types of integrals are called when you have an infinity up here? Starts with an I think, yeah. Probably been a while since Calc 1, I'm guessing. Do you remember the term improper integrals? Do you remember how we handled it when we have infinity up there? You turn it into a, yeah, it's a limit. You take a limit. So basically you turn this into something like, maybe you could use like an n, and then you take the limit as n goes to infinity. You turn it into a definite integral and then take the limit. So we'll be doing that a lot in the next section. But here's the thing. The big idea I want you to get out is this. That looks rather complicated. But once you evaluate the integral, what's going to happen to all the t's in here? what happens every time you evaluate an integral and you plug in the with this variable? What happens to that variable at the end once you evaluate it? Does it appear in the answer or not?
No.
No, it's evaluated, it's done. So is it fair to say that once we're done, this is going to be a function of s alone? Okay, yeah, that and that's what the transform is. It's a function of s. Okay. All right, so here's the idea. We're going to do a lot of hand waving here, and then we're going to get into this in later sections. But you know, this is the IVP we're asked to solve. Okay, and then that g function right there, remember that's piecewise. So Laplace transforms are actually really helpful with piecewise functions. So here's what happens. You're going to apply the Laplace transform to the entire equation, both sides. And in fact, you apply the Laplace transform to the initial condition as well, which is interesting. You actually apply it to the whole thing. And what ends up happening is this little x function is going to be transformed into a big X function. And this little g function is going to get transformed into a big G function. Notice the domains are different though, right? We're now in the S domain. Now the derivative is a little more complicated. We're going to do that, I think, in 7.3 maybe. We have to develop the math there. But basically what's going to happen there is it's going to translate into this function. So you'll just have to trust me on that. But you notice the initial condition? That's why this comes into play. Okay, so we'll just hand wave over that. That's what's going to happen to x prime. So what'll happen is once you replace everything in green, red, and blue up there, and use that initial condition for the green guy, what'll happen is you'll turn the equation into this guy. All right. Now, it turns out the Laplace transform is also linear, which is the reason why we can do this. We'll talk about what linear means later on. For those of you in algebra, it basically, actually, you guys have studied this, right? You can push linear operators through sums and through constant multiples of functions, but we'll talk about it again later on. It makes it a lot easier to work with. Derivatives are linear operators. You can push them through sums, you can push them through constant multiples. Integrals are linear operators. All right, and since the initial condition is x of 0 equals 30, we'll plug in the 30 there. And there we go. Take a look at that equation. Oh, let's do one other thing. Yeah, let's do that. Yeah. Do you notice there's no derivatives in there? Yeah, that's a huge relief, right? So why don't we do this? Why don't we solve for x, but let's solve for the big X, the version of x that's in the other world, in the S domain. So we're going to take this guy and solve for big X. All right, if you solve for big X, then you'll have everything on the other side. That's just very simple algebra. You guys can do that easily. And then at some point, we'll have to evaluate that G of S right there, the big G. You can use a Laplace transform table. And by the way, we're going to prove everything in the table anyway, so you don't get out of anything for free. But once you prove it, you can use the table. And so that little function G, where is it? If you plug this in or use the transform table, what you'll find is you'll get out this guy. It's not exactly obvious why. Again, we're going to do some hand waving here. So then what we'll do is we'll plug this in there. And then what we've got is our solution in the frequency, Laplace, or S domain. All right, so we'll simplify, and there's our solution. The problem is it's wrong, it's in the wrong domain. So what you have to do is transform it back into the T domain. So to do that, we'd use a transform table. In doing this, what's going to happen is for many of the problems, you're going to have to use, do you guys remember partial fraction decomposition? We're going to be using some of that stuff. So I'll probably set up a discussion where you have to do one of those. But that's the idea. And if you translate this back using the table, you'll get this guy. And that's the same solution that we got above. Okay, now it seems like I took the same amount of time on both, but you'll notice on the top one, I never even did the hard part, which was solving it, right? So this is basically just using tables. All right, and Laplace transform, super easy for constant coefficient stuff. You're going to use it a lot. So yeah, we're going to start from the basics. Okay, so here's kind of a visual as to the advantages of it. All right, so this is our old way of doing it. If you follow the black arrows here, we stayed in the t domain. We started with our differential equation. We stayed in the t domain, and this involved all of the different types of ways that we, methods we had for solving these things. So this one was piecewise, so we had to break it into subintervals. In each one of those subintervals, in this case, you'd use undetermined coefficients because we had that constant forcing term. So that kind of sucks. You have to find YH and YP. When you're finding YP, you have to take derivatives, so that sucks. If you're going to use variation of parameters, you'd use integrals. And then you have to fit the constants in order to get the functions to match, as we were talking about before. So it's a lot of work, and then you arrive at your solution, and that's fine. So basically what we do is we just move into the S domain. We transform the differential equations, more specifically the IVP. You have to have an initial condition. Using the transform, using tables, solve a simple algebra problem, and then use the tables in reverse to get to the solution. All right, that okay?